Okay, so we're going to start to look at the different gas laws. So if you could take out your reference table and flip to the very back of the reference table, it says combined gas law. P1 V1 over T1 equals P2 V2 over T2. I want to talk a little bit about what those variables represent. P, it tells you, is pressure, V is volume, T is temperature. Remember we mentioned in the last video that the temperature is always going to be in the Kelvin temperature, so we can't plug any values that are in Celsius into an equation. We're going to look at each individual gas law separate. So there are 3 gas laws: Boyle's law, Charles' law, and Gay-Lussac's law, and then we'll put them all together into that combined gas law. So the first one we're going to look at is called Boyle's law, and it has to do with when one of the variables, temperature, is held constant. When the temperature is constant, pressure and volume are inversely related. So we talked about that directly related means that as one goes up, the other one goes up, or as one variable goes down, the other variable goes down. But inversely means that if one goes up, the other one goes down. So when the pressure goes up, volume goes down. When pressure goes down, volume goes up. So if you were to look at that equation one more time on the back of the reference table, the P1 V1 over T1 equals P2 V2 over T2, when a question tells you something is going to be held constant, what we're going to do is we're going to put our finger over that variable. So since Boyle's law has to do with temperature being held constant, we're going to put our fingers over the T. So our equation just becomes P1 V1 equals P2 V2. P has to do with pressure and V has to do with volume. Here's a graph showing you what the relationship is for Boyle's law. So we have volume and pressure. Although we could have it opposite, it would still be the same relationship. This is an inverse curve. As the pressure gets bigger, think about, this is a graph, if the numbers are going up, so here down on this end, we'd have high values. So at big pressures, we have little volumes. And then when the volume's a high number on the graph, big volume, we have little pressure. So they are inversely related. As pressure goes up, volume goes down, or as volume goes up, pressure goes down. So what we want to do is be able to be given a word problem, and from the word problem we're going to show you how do you solve a question related to Boyle's law. So the question reads, the pressure on 20 milliliters of gas at constant temperature is changed from 4 atmospheres to 2 atmospheres. What is the new volume of the gas? So all year we've been really working on annotating or marking up our questions. So in this particular case, we want to underline our units because our units are really important. So we have 20 milliliters. Keep that in mind. We have 4 atmospheres and we have 2 atmospheres. We're looking for a new volume. So our setup here is going to be P1 V1 equals P2 V2. We know that the pressure is changed from 4 atmospheres to 2 atmospheres. So initially, before we get comfortable with these problems, it's a good idea to write out what our variables are. So we have P1, P2, V1, and V2. So the pressure is initially at 4 atmospheres, and it goes to 2 atmospheres. The volume is initially 20 milliliters, and we want to know what's the new volume. And then we're just going to take these values and plug them into the equation. So P1 is 4. We'll leave the units out for now. V1 is 20. P2 is 2. And V2 is our x. If you want to leave it as V2, you could leave it as V2. If you want to put an x, you could put it as x. So 20 times 4 is 80 equals 2 times V2. And then you would divide by 2 to get V2 all by itself, and we get V2 equals 40 milliliters. Okay, let's try another problem. So we have a sample of gas has a volume of 2 liters at a pressure of 1 atmosphere. When the volume increases to 4 liters at constant temperature, the pressure will be. So again, remember we want to annotate, mark up our text. This is important, the idea of constant temperature, because we have P1 V1 over T1 equals P2 V2 over T2. When the temperature is constant, we're just going to exclude it completely from the equation. So our equation becomes P1 V1 equals P2 V2. So let's write down what our variables are. So the volume is initially at 2.0 liters, and it says that the volume increases to 4 liters, so that's the new volume. When it was at 2 liters, the pressure was 1 atmosphere. Remember, atmosphere is abbreviated ATM, and they want to know what the new pressure will be. So plugging this into our equation, we have the initial pressure was 1. The initial volume was 2 equals P2 is our X, we don't really know, and V2 is 4. So we have 2 equals X times 4. Divide, because you always want to isolate your variable. So we have X equals 1/2 or 0.5 atmospheres. Next, I want to look at one more relationship. The next one is called Charles' law, and Charles' law has to do with pressure being held constant. When pressure is held constant, the volume and temperature are directly proportional, meaning that as one goes up, the other one goes up. So if the volume goes up, the temperature goes up. If the volume goes down, the temperature goes down. So we have this equation P1V1 over T1 equals P2V2 over T2, our combined gas law. And Charles' law has to do with when pressure is held constant. So this would be like putting your finger over the P, and we could remove them from the equation because it's going to be held constant. So our relationship is V1 over T1 equals V2 over T2. And these are direct. I remember that when you, in this case, direct, you would divide. So when you have to divide, like V, you would have to divide by T. That's a direct relationship. This is a depiction of what the relationship of Charles' law would look like. This is a direct relationship. Oops, sorry. So as the temperature is increasing, if you look at your graph, to the right, at a high temperature value, the volume is also high. So this is direct. As one goes up, the other one also goes up. As one goes down, the other one goes down. So let's look at an example. If 10 liters of hydrogen gas at standard temperature and pressure is heated to a temperature of 546, the pressure remaining constant, that's super important. We always want to circle or underline when something is going to be constant. What is the new volume of the gas? So our equation is P1V1 over T1 equals P2V2 over T2. If the pressure is constant, that means we can eliminate pressure from the equation. So P comes out. So now our equation is V1 over T1 equals V2 over T2. Just like we did with Boyle's law, it's good if we could write down our variables. So we have V1 over T1 equals V2 over T2. So let's write out what everything is. Okay, so our initial volume is 10 liters of gas. We want to know what the new volume is, so that's our X. It was originally at STP, so our original temperature, we have to look at the very front of our reference table. It says 0 degrees Celsius or 273 K, and it's heated to a temperature of 546. Now here, remember, it says 0 or 273, but we have to use the Kelvin value. So taking the variables and plugging them in, we have 10 over 273 equals X over 546. You get to do your favorite thing in the world. We get to cross multiply. And when we do this, we should end up with 20 liters. So since the initial volume was in liters, the final volume is in liters. Sometimes we have mistakes like where students will write one is in milliliters and put the other one's in liters, or one is in liters and put the other one milliliters. Make sure the units are consistent. If this is liters, that's liters. Meaning if V1 is in liters, V2 is in liters. If V1 is in milliliters, V2 should be in milliliters. Okay, the last example we're going to look at is another situation where we have the pressure remains constant. So we have our equation, P1V1 over T1 equals P2V2 over T2. Pressure is constant, goodbye, it's out of the equation. So we have V1 over T1 equals V2 over T2. Again, it's nice to list out your variables just so that when you go to plug them into the equation, you don't make a mistake. Some people are going to start to skip this step as they'll just plug them in right away. So the volume is initially at 1 liter. It's at STP, which remember is on table A. It tells us it's 273. We have to have it in kelvins. So it will be 273. They say the volume is the temperature is raised to 547 Kelvin. The new volume, well, we don't really know. So let's plug it in. V1. Let's put them in here. V1 is 1. T1 is 273 equals V2 is X. T2 is 547. Your favorite thing. We get to cross multiply. Okay, so let's do. And we end up with our answer is 2 liters.